Right guys, this week the UK government's guidance on what to do if you have asymptomatic COVID has changed. If you take a lateral flow test and the result is positive, you don't need to take a confirmatory PCR test, you can just trust the result. They've done this to reduce the strain on the PCR testing system. And they've said it's because COVID is more prevalent in the community, therefore we can rely more on the lateral flow results. Is that the case? That's what we're going to ask today, and we're going to use Bayes Theorem to find out. Now, Bayes Theorem is a way of turning around conditional probabilities. So, I mean, what does that mean? We're going to define conditional probabilities. We're going to then define Bayes Theorem, sort of do a little quick derivation of it, and then we're going to apply it to some figures, some real world figures from May, that's when the cases were the lowest, to January, that's when cases are highest. There are about 200,000 daily cases now, I think. And then we're going to compare asymptomatic cases and symptomatic cases and see how reliable a lateral flow test would be in each of those scenarios. Okay? So Bayes' theorem is a way of turning around conditional probabilities. So what is a conditional probability? Well, a conditional probability is the probability that something happens under the condition that something else has happened. For example, you might ask, what's the probability of rolling a 2 on a dice given that the result is even? So if we say x is the result of the dice roll, we're asking what is the probability that x equals 2, and then we use a vertical line and say it's given that x is even. Okay? And we're asking what that is. Now if you ever think, if x is even, it's either 2, 4 or 6. It's a standard dice. So the probability that x equals 2, these are all equally likely. Therefore the answer to this is a third. So that's a conditional probability. The way of working these out in general is we use, well, let's draw a Venn diagram here. Here's A, say, and here's B, and this is A intersect B. Okay, and we say the probability that A given B is equal to, well, we're only concerning ourselves with B having happened, so it's this proportion here divided by the entire proportion there, the entire space there. So this is the formula for a conditional probability, okay? And we're going to use this result to derive Bayes' theorem. Okay, so there's nothing special about A and B here. I can write this the other way around if I wanted to as well. Well, A intersect B is the same as B intersect A, so I can write it the same way around. Get a bit messy there. Over probability of A. It's the same result, just swap B and A round, okay? Now if we multiply up on both sides, we get probability of B times the probability of A given B equals A intersect B. And on this one, we have probability of A given A equals probability of A intersect B. So these two are equal because they're both equal to that. So let's write this over here. We have probability of B, probability of A given B is equal to probability of B given A times the probability of A. Okay, that is equal to that. Now we can divide through by the probability of B, so we get probability of A given B is equal to heads running out, getting too excited, writing too quick. And this here is Bayes' theorem. As you can see, we have a conditional probability one way round, and this way it's turned around, it's the other way around. So that's what I mean when I say turning around conditional probabilities. Okay, this is a crucial result. I'm going to write this up the top here. Right, so first we're going to look at just the lateral flow test. We're going to pretend PCR tests don't exist, and we're going to compare May last year to January this year. In May there were around 2,000 cases a day. In January, roughly 200,000 cases a day. The lateral flow test has a false negative rate of around 20% and a false positive rate of around 0.3%. They're 99.97% accurate, okay? And I've put the population of the UK as 60 million. I'm not sure what it is, but again, it doesn't matter for our purposes. We're only illustrating Bayes theorem today, okay? So what I want to know is, if you get a positive result, what is the probability that you have COVID? Okay, so what is the probability that you have COVID given that your lateral flow result is positive? Okay, and this is where we use Bayes theorem. I've got it up here, look, keep referring to it. So we need, if A is COVID, B is positive, the probability of getting a positive result given that you've got COVID. We want the probability that you have COVID, and we want the probability of a positive result. Okay, now the probability that you get a positive result given you've got COVID is 1 minus this, or 100, so 80%. Okay, if you've got COVID, you'll get a false negative 20% of the time, which means you get an accurate positive 80% of the time. The probability that you have COVID, now in May, was 2,000 divided by 60 million. Okay, that's just a general case, regardless of whether or not you've taken the test. That's the probability of having COVID. And the probability that you get a positive result, well, either you have COVID and you get a positive result, or there's a second option, you could not have COVID. There's a strong probability of that happening. What is that? Not enough zeros yet. So that's the probability you don't have COVID, but you still get a positive result. Well, the probability of that happening was 0.03%. That's percent, so it's 0.0003. Okay. Right, so now we've got this, and this here, so we can put it into this formula, and this gives us 0.8, which is that one, times this one, which is probability of A, 2,000 over 60 mil, divided by this thing here. I won't write it out again. This gives us a figure of 0.0816 equals roughly 8%. Okay, so that might be quite a shocking result to you if you think you've got a test that's 99.97% accurate, and then you get a positive result from it. You've still only got an 8% chance of actually having COVID. Now the reason for this is because the cases in the community are so low. 8% compared to whatever 2,000 divided by 60,000 is, 60 million is, your chances have increased dramatically of having COVID, but they are still low overall. Okay, you're just probably one of the false positive people, because the real positive people are so rare. Okay, now if we compare that to, I shouldn't rub it all off, we can use some of this. Now if we compare that to January, all we've got to do is put a couple of zeros here. What does this become? 800, 598,000, and work this out. We get a new result. Just pop it in your calculator. 0.899 equals 90%. Okay, so just if we're just relying on lateral flow tests, in last May they would have been pretty unreliable, but now that if you get a positive result, there's a 90% chance you have COVID. All right, so yeah, it looks like using this data, the government is justified in not requiring the PCR tests. All right, so now let's look at the comparison of symptomatic cases with asymptomatic cases. So if about 35% of COVID cases are asymptomatic. So of that 200,000 from this January, these are the January results, by the way, 70,000 will have no symptoms. That means 130,000 will have symptoms. And I've made up this figure. 500,000 will have maybe a cold or the flu, and will have the similar symptoms, a cough or whatever, which means there'll be 59,300,000 with no COVID, no symptoms. Okay, so let's look at these two cases one at a time. First of all, let's look at the let's ignore this one and look at the cases with no symptoms. We can just imagine we have one now single population with 59,370,000 people in it, and again we want the probability, let me use the green for that to keep consistent, the probability that you have COVID given that you get a positive result. So again we're using the same three things. We want this, we want this, and we want this. Okay, the probability that you have a positive result given you've got COVID is the same. It's 0.8 because of that false negative rate. The probability that you have COVID at all is 70,000 divided by this isn't, it's, what is it, 593, we had the 7 because we're looking at the total population. How many zeros have I got in there? Yeah, look. And the probability that you're positive at all is you've either got it and you get your positive result, or you don't have it, which means you're part of these 59 million. And you get a false positive. What was that? 0.00003 again. So it's the same calculation pretty much. And if you put that in your calculator, you get a figure of 76%. So it's dropped down a bit. That's because proportionally there are fewer positive cases without symptoms compared to overall positive cases. If we do the same calculation using this population, now you can see there's a big proportion of this. There's only 630,000 people in this population, and like what, 20% of them are have COVID. So we're going to get a much higher result. If we put the figures in, I'll let you go through it. We get a figure of 99.86%. Okay, so that's if you were to do a lateral flow test with symptoms, you could be 99.86% sure that you actually had COVID if you got a positive result. So why is it that the government have said the less reliable lateral flow results, you don't need to take the PCR, and the potentially more reliable lateral flow results, you do have to take a PCR instead of taking a lateral flow? So there's two reasons I can think of. If symptomatic cases were more transmissible, for example, you might not find this 20% false negative rate acceptable, and you might want the more accurate PCR test to reduce the amount of undetected positives going back into the community. Another reason could be symptomatic cases are more likely to develop into variants of concern, so you want to keep tabs on the genome, make sure you can keep track of any changes. But otherwise, yeah, that's still quite a high success rate. So they are justified, compared to May last year, they're justified in just relying on the lateral flow tests, I think. But anyway, that's it for today. We're going to be coming back to Bayes' theorem quite a lot. It's a very useful theorem. So I hope you enjoyed it. I'll see you next time.